Hello, I just wanted to go over an example that we're considering in our course. This is an example of application of Navier-Stokes equations, and generally to give a sense of what a boundary value problem looks like, how simplifications and underlying assumptions come into play. The example we're considering is the liquid flow down an inclined plane. So we are interested in the distribution of velocity in the liquid film, and it's bounded on the bottom by a solid plane and on the top by a gas. So the boundary conditions for the velocity profile in the liquid film would be no slip and impermeability at the wall and zero shear stress at the free surface interface. The governing equations are going to be the continuity equation du dx plus dv dy equals 0, so the fluid is considered incompressible in 2D, and the x direction momentum equation will be du dt plus u du dx plus v du dy on the left equals to minus 1 over rho times the pressure gradient in x plus nu times second derivative of u with respect to x plus second derivative of u with respect to y. That's a viscous dissipation term. And not to forget, the body force would be g times sine alpha, where alpha is the inclination angle of the plane. The y direction equation would be simplified greatly by employing the fully developed flow assumption. And the fully developed flow means that in the main direction of the flow, there are no changes of any flow parameters. In our case, the coordinate system is set up so that y-axis is normal to the plane and x-axis is tangent to it in the direction of the flow, so downwards. And the fully developed flow assumption tells that there are no changes in x. So d by dx of any flow parameter is equal to 0. If we use that in the continuity equation, we immediately arrive at the parallel flow assumption that we could make a priori, but we actually don't need to with the fully developed flow, because if there are no changes in x, then in the continuity equation du dx is equal to 0, and therefore dv dy is 0. So v is a constant in y direction across the fluid layer. Remember, there is an impermeability condition at the wall, so v velocity at the wall is equal to 0. So v is a constant from continuity equation across the layer, and it's that constant is equal to 0 at the wall, so v is equal 0 everywhere. So with the combination of the fully developed flow and the impermeability of the wall, the y direction momentum equation reduces to 0 equals minus 1 over rho dp dy, plus the whole viscous dissipation term is 0 because v velocity is 0 there, minus g cosine alpha. That's the y component of the gravity term. If we integrate that equation, we arrive at p equals minus rho gy cosine alpha plus some function of x. And we need to specify pressure at the interface. If, let's say, it's p0 at y equals h, which is our free surface, then we have expression for pressure, p equals p0 plus rho g times h minus y cosine alpha. And note that the dp dx, the gradient of pressure in the x direction, is 0. So this flow is entirely gravity driven. It's not the pressure driven flow. Now if we go back to the x direction momentum equation, that simplifies too, now that we know that v is 0 and there are no changes in x direction. So what remains of the x equation is mu times second derivative of u with respect to y equals minus g sine alpha. If we integrate this equation twice with respect to y to find u, we arrive at, and substitute the boundary conditions. Remember, there is no slip, so u is equal to 0 at the wall, and the shear stress equals to 0 at the interface with the gas at y equals h. The shear stress in the x direction is mu times du dy at y equals h. Mu is viscosity, but the derivative of velocity should be equal to 0 with respect to y, so it kind of comes up vertically. The velocity profile comes up vertically at the interface with the gas, so 0 shear stress. So when we integrate the x direction equation twice, substitute these two boundary conditions to find the constants of integration, we have our solution. U is g over 2 nu times y times 2h minus y times sine alpha. So that's the expression for the velocity profile in the liquid film in the x direction, and in the y direction normal to the wall, v equals 0. So combining that with that expression for pressure that we had, we have the full solution. So that's going through that example, again illustrating the implementation of some assumptions to simplify the Navier-Stokes equations, and making use of the boundary conditions to evaluate the constants of integration once we find the solution itself.